So my name is Alessandro. I'm the second instructor in this course. Okay. I work in not in algorithms. I work in cryptography, complexity theory, and security. Okay. And I'll be teaching the next few lectures. Also, does anybody know how to turn off the projectors? My first time teaching this particular room, and there's a lot of buttons there I could push. I didn't want to push about the ones about the light, otherwise people might just fall. But now you're all seated, so we can play with the. Does anybody know? Let me try this one because it looks like a scary one. Thank you. Ah, there's a touch screen even. Okay, didn't even see that. Wonderful, thank you. Okay, you have an A+. All right, so last time Satish sort of had mostly introductory lecture, but you did get to see some concrete things, right? So if you remember, you got to review some asymptotic notation, and also you saw an algorithm for multiplying integers that was faster than the sort of school book one, right? So today, the plan is we're going to talk a little bit more about sort of divide and conquer algorithms, such as the one that you saw last time. And because divide and conquer algorithms are going to show up a lot in the next few lectures, we are going to have to first spend some time to talk about recurrences. These are recurrences that show up when you try to analyze the running time of recursive algorithms, okay? So let's just, maybe I should use the big chalk. I just recall from last time. So if we have two integers x, y, okay, there was an algorithm that you saw last time to compute x times y. Does anybody remember what it was? Yes. Yeah, you had your hand up. Yeah. Good. So, okay. So the first realization was to say, look, x and y are both integers. We can look at their bit representation and slice them in half and look at the left bits and the right bits. Okay. You can think about this as basically saying, take the high order bits. This doesn't really write. Take the high order bits of x, multiply them by 2 to the n over 2. Add to that the low order bits of x, so that's the same as x, right? And take the high order bits of y, add to that the lower order bits of y, okay? And this is, I'm just rewriting the same expression. This is just x, and this is y, okay? And if you open it up, this has it looks like a recursive algorithm, okay? So it's 2 to the n times xl, yl, should I write larger? Okay. Looks large from here, but probably not from the back of the room. Let's try that. Okay, maybe not that much. Yeah. So 2 to the n times xl, yl, plus 2 to the n over 2. And then here we have a cross product, right? This one and that one. Okay, so, this really doesn't write. Let me try this other one. xl times yr plus xr yl plus, this is the leftover ones, xr times yr. So this is a recursive algorithm because I can find inside it subproblems of the same problem that I started with. One subproblem, two subproblems, three subproblems, four subproblems. All of these are integer multiplications that involve integers that are half as big as I started, okay? So, and you saw that this gave rise to a natural algorithm whose running time could be described as a recurrence. There was T of n times that equals what? What was the recurrence? Yeah, 4 times Tn over 2. Why? Because we have 4 subproblems of half the size that we started Okay? But then we still have to combine the subproblems, okay? And this is just integer addition, which is linear, okay? And what was the solution of this occurrence? So this is just review and squared, right? Which wasn't a super interesting way of achieving a recursive algorithm because it is sort of the trivial running time that you get by just having every digit multiplied by every other digit, okay? So, but there was a way to tweak this algorithm to achieve something more interesting, okay? And so it doesn't really matter exactly how it was. Let me maybe remind you of it. Instead of taking this expression, the sort of new idea was to still recurse, but recurse in a smarter way so that instead of having 4 subproblems, you have just 3 subproblems, okay? And I'm going to try one of the bigger ones. Let's see if they're here. No? Maybe next time I should bring my own. So the new idea was to say, let's have 3 products that are computed. One of them let's call P1, the other one called P1, P2, and P3. But here in the middle, you put P1 minus P2 minus P3, okay? And here you put P3. What are these 3 magical products? Well, P1 is just the product of XL and YL. So this matches this here. P3 is just the product of XR and YR. And P2, well, let's see. Here we want to get the 2 cross terms, right? So what should I get? I can consider XR plus, so XL plus XR times YL, YR, right? So this will create these 2 expressions which cancel out, and they leave you with the cross products, okay? Which are the ones you wanted to have here. This convoluted way of writing it, okay, achieves the goal that now I only have 3 subproblems, okay? Because each of these is one product. Here's one product, here's one product, here's another product, okay? And with just computing 3 subproblems, I'm able to achieve the same expression that I cared about earlier. Okay, so, well, big deal. Now this 4 becomes a 3. But it actually is a big deal because it actually changes the running time. So last time I believe Satish asserted the running time but didn't justify it. And today we're going to see what is the actual, see why it has the running time. Does anybody remember what was the new running time? So n, so I'm just guessing that you said the right answer, n to the log base 2 of 3, okay, which is on the order of n to the, I think, 1.58 or something like that, or 5.9. Either way, it is definitely less than 2 because you would need to write 4 here in order to get 2 in the exponent, okay? So it's clearly less than 2. Okay, so all of this is as a reminder that first, you need to understand divide and conquer algorithms, you need to be very familiar with this recursive recurrence relations on running times. So I want to take the first, I guess, half of today's lecture to just talk about that, okay? And then we're going to see how, after talking about that, it's going to be easy to just eyeball the running time. Yes, there's a question.
I think there's a slight typo. For the coefficient of 2 to the n over 2, it should be P2 minus P1 minus P3.
Sorry, yes. Thank you. Yeah, because we want to have the big product here, and we cancel out P1 and P3. Thank you. Good. All right. So what I wanted to do now is talk about recurrences. And in order to do that, we need to first recall a couple of useful facts that we'll keep using. Let me give this guy another shot. So some useful facts. So suppose I have some integer a, and I raise it to the b, and I raise it to the c. Okay? So I'm exponentiating it twice. This is the same as if I first exponentiate by c and then by b, right? Very simple thing, right? Both of them equal to a exponentiated to the b times c. Why? Because this is just saying, please multiply a b times, do that thing c times, right? And since multiplication commutes, then both of these equal this one, so they're equal. OK, let me write something a bit maybe less obvious. So I can claim that a to the log b, say, c, equals c to the log. Man, this guy is such a rebel, doesn't want to do what it's born to be. OK. Does anybody believe this equality? All I'm doing is I'm just leaving the log b here. I'm just switching the base and what's inside the log. That feels like such a funny thing to do, right? Who believes it's funny? Yeah, it is kind of funny, right? OK, but so let's convince ourselves that this is the case, because this type of tricks show up all the time when you think about recurrences, OK? So does anybody have any suggestions on how I can justify this equality? Yes? I could take the log of both sides. That's fine. Another way to view it is to kind of refer back to this one, which I just talked about. You can just, yeah, you can take the log of both sides, and then it would be easy. Another way to do it is you can say, well, what is a? A is just b to the log b a, right? That's just the definition of what is the logarithm, right? It's like saying, what is n? N equals 2 to the log n, right? It's the same thing. What is a? A is the same as b to the log b of a, right? It's just that I'm not fixing the base to be 2. It's just the base now is b, OK? So, OK, that was just a, OK? So we still have log b c, OK? But notice, these are two exponents, right? They commute. I can put this guy inside and this guy outside, right? So this is the same as b to the log bc, and then everything to the log ba. But what is the thing inside the parentheses? C. OK, good. OK, so all of this is trivial. OK, let me maybe go to something less trivial. This is my last name. How do you pronounce it? Maybe this you didn't know already. Any takers? Yes? Yeah, good. OK. So it's a trick question, right? Because CH in two languages that are pretty common around here, both English and Spanish, CH goes to ch, right? And I get that all the time, chiesa. No, but it's not, it's chiesa. Okay? So in Italian, CH is a K. OK, well, if you didn't learn anything here, at least you learned that. So don't spell it like this. This is just a suggestion of how to read it. OK? OK, so what I want to do right now is I want to work sort of our way up to reasoning about general recurrences. OK? In order to do that, I want to try to construct a mental picture of how a recurrence looks like. So I will start with a familiar recurrence whose answer we understand, that one there. OK? So whenever you write T of n is, say, 4 times n over 2 plus order of n, in your mind, you should think about of some tree, right? So because this is representing a recursion, right? So the recursion means that you start at some node, you have these subproblems, these subproblems have their own subproblems, right? So it's one big tree until you hit the bottom, right? So it's also helpful when you analyze the recurrence to kind of strike out the big O notation and just introduce some concrete arbitrary constant, say C. OK, so C is just some constant that bounds the linear running time here. So what you have is a work tree that says, OK, I'm going to work this much here. Why? Because I worked T n over 2 4 times in subproblems, okay? And in combining, I paid then C times n. And in turn, these guys sort of give rise to 4 subproblems of size n over 4. And say, OK, fine, everything is trivial. Yeah, I agree. It's not very difficult. That's why it's an undergraduate course. So let's try to do some accounting here, OK? So at the very top, we have one problem of size n, OK? So the cost at the very top is going to be one problem. So it's n at cost C times n. OK, so we have one problem to kind of, we have to combine these things. We pay C times n once. OK? But now we have to account for all the costs that are lower down in the tree. OK, so we're going to do this carefully, because later we're going to have to do it in a general setting. Okay? So it's easy to kind of build intuition, a concrete example. How many problems do we have in the next layer of the tree? 4. OK, 4 problems of size. Now it's n over 2. What's the cost? What? Each one. So at cost, each at cost. Okay, so I want to say each. Okay. So it's going to be C times whatever the problem size is. Okay, C n over 2. Okay. Now, of course, we have 4 problems. So really, what we should care about is the total cost across the layer, right? So here it was 1 times Cn, right? Now it's going to be 4 times C times n over 2, right? That's the cost in the second layer. Now, if we go further down, we're going to have 16 problems of size n over 4 at a cost each, which is what? C times n over 4, okay? And the total cost is going to be 16 times C times n over 4, okay? Now, in general, when we are at layer, say, I, because we have a fan out of 4 each time, we're going to have 4 to the I problems of size n to the, divided by 2 to the I, right? Because we divide by 2 each time. Notice that the fan out and how much we divide, those are different constants, right? So there is a 4 in front here, which is different than the 2 below, right? So it happens that one is twice the other, but it doesn't have to be. It's just a recurrence, right? So those are 2 different constants. So there's a 2 here. At the cost, C times n divided by 2 to the I. Why that? Because the cost is linear. It's C times whatever the problem size is. So overall, what we have is 4i times C times n to I. Now, these are the cost per layers. What is the total running time that is kind of the solution of this recurrence? The sum of all these things, right? So kind of TON is the sum of all these. OK, so let's sum up all these guys and verify that indeed, if you sum them up, you get something that is O of n squared. OK? We're going to do this once and then maybe tweak the example a bit to see how it's different. And we're going to try to generalize to an arbitrary recurrence. OK? So all right, so the sum. Now, there is a nice way to write this. We have a common term across all of them. What is the common term? Yes, and C times n, right? So C times n, we take it out. And inside, we have a sum of how many terms? Yes? log base 2 of n terms, okay? So we have 1 plus the next term, we can view it as 4 over 2 to the 1, right? That's whatever is left of there, right? Plus 4 times 2 to the 2, right? This evaluates to 4, which is consistent with here, right? 16 divided by 4, right? Plus blah, 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 right? So in the ith term, we will find 4 to the I divided by 2 to the I. Sorry, 4 over 2 to the I. And then at the very end, what we will find is 4 over 2 to the log base 2 of n, okay? Why log base 2 of n? Because after we have halved n log n 2 times, we get 1, okay? And that's the base of the recursion. So, okay, so that is the expression. Maybe we should simplify it a little bit to understand it better for this particular case. So it is 1 plus 2 plus 4 plus blah, 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 all the way up to, what is the last term here? N, right? Because it's 2 to the log 2 of n, right? So that's n. Okay. So, so basically here we're summing 1 plus 2 plus 4 is log n times. We get twice as much each time. Or another way to view it is that we start with n, and we sum to it its half, and we sum to it its quarter, right? And so on and so forth. Now, what is a good bound for this expression? Yes, there's a question.
I actually have a question.
Yes.
Why is this in the log base 2?
Okay, good question. So every time we go down a layer, our problem size halves, okay? Now, if we start, say, with problem size 16, we halve it, we get 8, then we get 4, then we get 2, and we get 1. Once we have a problem size of 1, that's a constant size problem. We can solve it kind of trivially, right? So how many times we halve n, that's precisely the definition of log 2 of n, okay? Yeah. Right, thank you. So what is so now we just need to understand this expression. What can I bound this expression by? Yeah? 2n, okay, that's a good way to view it. And one way to remember that is the fact that if you take 1 plus 1/2 plus 1/4 plus 1 over 8, and in general, this is always no more than 2, right? So it's the same is happening here. You have this n here, and you're adding to it a half and a quarter, right? And it's just that thing scaled up, right? So this is at most Cn times 2n, which is order of n squared. By the way, a sloppy bound that you could have used here would have been to say, OK, each one of these is individually no more than n, and I have at most log n of them, right? That would have been a bound, just not as tight, because you would have gotten n squared log n, right? Whereas realizing that this is the case gives you this 2n, gives you a better bound. OK, so far so good. So we have verified that that recursion has a sort of a running time or a solution order of n squared, OK? I encourage you to kind of, the first few times, maybe to write this tree, because then you can paint it in your head on the fly, and you have a good sort of concrete, sort of intuitive feeling of how the recursion behaves. Now let's change the recursion slightly to the other one. We put a 3 instead of a 4, and see what changes in our bookkeeping, and what causes the eventual running time to change. Okay, so, and then after that, we'll be able to spot the pattern. Okay, sounds like a reasonable plan? Okay, just to make this time efficient, if you'll excuse me, I will go back and actually change things directly on the things I've written, okay? So pay attention to how I change stuff, okay? So let me move this up. By virtue of being up there, it will be outdated. And now we start again here. And I'm going to maybe try to box the things that I change. So our first change is going to be no more 4 here. It's going to be a 3. Okay, so we have changed this. Now the recursion is different. Notice that I haven't changed the constant that determines how much smaller the problem gets from one layer to the next. Okay, I'm leaving that one the same, and also this one the same. Okay, in fact, here, let me just clean it up a little bit. We just put a nice C times n. Okay, this is the same as before, just written a little bit more cleanly. Okay, so we have a 3 here. So what changes? Well, first, the picture changes. We have one less branch here. Okay, so okay, so that branch is not here. Gone. Okay, but so that was just a picture, right? So what we cared about was the bookkeeping itself, right? So in the bookkeeping, what changes here? First, number of problems. You have fewer sub-problems. Clearly, the fan-out, instead of growing by 4 each time, it will grow by 3 each time. Okay? So we don't have 4 here anymore. We have 3. Okay? We don't have 16 here anymore. We have 9. We don't have 4 to the I anymore. We have 3 to the I. Okay. Okay, so far so good. Now, the problem size, does it continue, go from n over 2, n over 4, and so on and so forth, like before? Yes, okay. What about the costs? They're the same, right? We're doing the same work per problem, just we have fewer problems. The tree kind of shrunk a bit, okay? But the cost is the same, right? Maybe the constant C is different, but C is just a symbol, just a symbol for us to keep track of what's happening, okay? By the way, here I was also assuming that T of 1 itself is C times 1, right? So maybe the base case is a bit special. Just say that it's the same constant C at the very end. To the extent that this constant for the recursion and the constant for the base case are different, maybe C and C prime, just think of C as the maximum of the two. Okay, so you can, without loss of generality, assume that they are literally the same. Because we're doing, anyways, asymptotic analysis. Anyway, so nothing here changes. Now, of course, we have fewer problems. So when I account for everything here, my expression here changes, right? So instead of having 4 times Cn over 2, I will have 3 times Cn over 2. Here I will have 9 times Cn over 4. And here I will have 3 to the I times Cn over 2 to the I. Are we done with the bookkeeping here? Is there anything else I need to change? I don't think so. I think it's up to the, unless I made some mistake, but I think it should be fine. Convinced? Okay, so let's put this up there. And now let's see what happens in the when we sum up things here, okay? So Cn is still common to everything, so we can still pull it out, okay? And we're left with some geometric series, okay? Except that now the value in the geometric series has changed. What is the value that I should put in parentheses now? 3 over 2. Okay, so let's do that. So we have, again, I'm still boxing things that I'm changing. It's a 3 here. It's a 3 here. And there's a 3 here as well. Okay? All right. So, but now, I don't know, it's a bit like more awkward here what's happening, right? So we have 1.5 and then 1.5 squared, right? And at the very end here, we have, by the way, what do we have here at the very end? We have this right at the very end, right? Divided by n, sorry. Okay, so how do I understand this, this geometric series? Like this, I mean, it feels similar to this, but it's not the same, right? So does anybody have any suggestions? So now I kind of need to put something here, right? Yeah, we could use that one. And in fact, there may or may not have been already a homework around geometric series and big O notation. Has there been? OK, excellent. So you will prove on your homework what happens when you have a geometric series, OK, like this one, with asymptotic notation. Now, of course, part of proving it is using the exact formula. There's an exact formula to understand what happens in a geometric series. Okay? But at a very high level, it is intuitive to let's just kind of talk about it here. If you're summing up a bunch of things, let's call the value v, 1 plus v plus v squared, and so on, up to v, I don't know, m, OK? And, or maybe we call it, yeah. Yeah, let's do like that. And v is bigger than 1, which is what's happening here. Here, notice that the value that we're summing up is 1.5, right? It's bigger than 1. Then this entire expression is big O of v to the m. Namely, the last term dominates. OK? Somehow, of course, the other terms will contribute, and they will actually give you a concrete constant in front, like the 2 here was there. It was there because there were the other terms. But it doesn't change the asymptotics of it. OK? Now, there are 2 other cases. When v equals 1, this entire thing becomes what? Order of m, right? Because you're just summing up a bunch of 1s, right? And if v is less than 1, then the first term dominates. Like the other ones are just adding to it, so it's order of 1. OK, but right now, we are in this case right here. OK, and you will prove this is the case in your homework. So what should I write here? The last one, whatever is written there, right? So, by the way, so is everybody convinced that this was the last term? Right, because I just take 3 to the log 2n, and I do this switching trick here, right? And then I do the same switching trick on the bottom. OK? OK, so the last term is n to the log 2, 3 divided by n. The n cancels. OK, we get order of log 2, 3, which is what was claimed over there. OK? So now you have a justification that that particular recursion results into this particular running time. OK? All right, we're about to look at the general case. Are there questions about this specific case? One back there, yes. So can you speak louder? Here? Yeah. It is the same as this term here. In the numerator, there is n to the log 2 of 3. And the denominator is n, okay, which comes from this term. More questions about this before we move on? OK, so now we want to look at the generic recursion. While I write down the tree, you can stare at 2 more words. Maybe some of you guys know what these words are, but you can think about them. Maybe you cannot even see them. There we go. All right, so now we want to come back to those words in a moment. But so now we're going to look at some generic recursion where the fan out is A, the factor of reducing the problem by B, okay? And the cost to combine will be some n to the d. Okay, so now the constants here we have A, B, and D. So let me draw it. OK. What is this? It's a red wine from Tuscany, okay? And how do you say it? Chianti, not Chianti, okay? Chianti. For the same reason that it's Chiesa, okay? What is this? It's a harder one, right? But you should know. Who has kids? You probably might know if you had kids. It's actually an Italian company. They make strollers or like, how do you say it? Like all kinds of, you know, when you feed them or, it's called chicco, okay? It actually means grain, like grain of rice. So it's not chico, okay? So 2 more words. For the same reason, CH, CH here.
Why did you divide by n on the last term?
Here?
Here or the other spot?
Well, oh, because here, the numerator accounts only for the 3 to the log 2 over n. I also have a 2 to the log 2 n. Okay, so there's an n there I need to account for. Okay, so does everybody agree that this is a generic form of the recurrence? Right? Like we could try to generalize it even more, right? There are more general expressions of recursions that could show up in analysis of algorithms, but this is a concrete family of recursions that will show up in this course. And you should be able to kind of understand this. So now the fan out is A. Each time the problem becomes smaller by a factor of B. And now, when you combine the problems, it's not just a linear cost. It's going to be some polynomial cost, n to the d. And in fact, maybe here I want to, again, not use big O, but just use some c times n to the d. Okay? So now we want to say, given a form, a recursion given in this form, can I tell you the running time? Always, like, regardless of A, B, and D. Okay? So that's the goal right now. Okay? All right, so, but we know how to solve it, right? We just need to kind of carefully do this bookkeeping, okay? And then look at the very end, what is the sum of work across all layers of the tree. And ideally, once we get there, we'll understand what expression to write down, okay? So let's start from the top here. We have one problem of size n at cost. What's the cost? C times n to the d. Okay? All right, so now we have, I'm getting pretty close to this guy. So then we have, what is the next number of problems? A, right? Not B, right? So we have A problems of size, what's the size? N over B. At the cost, so what's the cost now? C times what? So we have to take N over B and raise it to the D, right? Because now it's not a linear cost, it's a polynomial cost of some sort. Okay? Okay, then we have A squared problems of size N over B squared at cost C times, now my problem size have gone smaller, B squared, and everything to the D. Okay? Now you see the pattern. So let's kind of make the pattern explicit. At the ith layer, we have A to the I problems. Now I have a problem because the chalk, the only big chalk is, has become very small. So A to the I problems of size, what's the size? There's a box with chalks? What?
On the bottom part, you can slide it out.
Yeah, no, but these are there's plenty of the small. I will start using the small ones. These are the fat ones. The right a bit bigger. So I will have to start using the thin ones. So it's n divided by bi. Okay. Okay. At the cost of c times n b to the I d. Okay? Seems like it is a straightforward generalization of the bookkeeping that we did there. Let's make sure we can actually account for the, okay, now comes moment I have to switch to the other chalks. So now we actually have to do the accounting per layer, right? So at the very top, we have one problem at cost c times n to the d. Okay, so we just say 1 times c times n to the d. Okay, fine. Next time, we have a problems at the cost of c times n to the b to the d. Okay, so a times c times n divided by b to the d. Agree? Okay. Then we have a squared times c times this expression right here, n divided by b squared to the d. And the pattern is that we have a to the I times c times n divided by b to the I to the d. Okay? So these are the costs at each layer. Yes?
Aren't you losing the n over b term?
N over b term. So it's here, right?
Yeah, I mean like the term in the middle, like a problem of size n over b at top.
Yeah, but so this size here, it's just influencing what I put in the parentheses here, right? So I am specifying the size because I take that size and I plug it into this expression. Okay? So this one kind of that's why that's the connection, okay? Good question. Okay, so now we're almost there really. Like we have figured out the cost at each layer of the tree. We just need to sum them up and figure out what they sum to, okay? So let me put this up, kind of analogously to the other one. Okay, so we have to sum up those guys. So what is the common term that I can pull out from everything? Before it was Cn. Now what is it? Cn to the d, right. Good. C times n to the d. All right. Now, in the first term up there, I am left with an easy 1. What am I left with in the second term? A divided by b to the d. Okay, that's what's left. Do you agree? Okay, some people agree. So what's in the next term? So in the second term up there, I pulled out Cn to the d. What am I left with? Right, so it's a squared divided by b to the 2d. Right? But there is a way to write it that is suggestive, which is I write still a divided by b to the d, and I square the entire thing. Right? And it seems to be a sensible thing to do, because if I look at the ith term, it looks precisely like that. It is a divided by b to the d, everything to the I. That's the ith term. Right? You can see it down there. Right? So I've pulled out c and n to the d. I'm left with a to the I. Here it is. And b to the I to the d, which is b to the d to the I. Okay, so that's my ith term. So that's kind of the pattern. I still need to figure out where do I stop. For what I do I reach the recursion at the bottom of the recursion? Log base b of n, right? So here we're going to find a divided by b to the d, everything to the log base b of n. Why base b? Because I am dividing n by b at every time, at every recursion, instead of 2. Okay? So I'm paying here, so as b increases, I will reach the bottom of the recursion faster. Okay? We just need to understand what is this expression. So, well, now, so before we had concrete terms, so we could argue about the expression. Now we have these variables, a, b, and d, right? So we cannot just give one form to this expression. It depends on what is r, a, b, and d. How many cases should I analyze? 3. They are these ones, right? So kind of the v here the role of v here is being played by a divided by b to the d, right? So it really depends. If a divided by b to the d is, let's say, greater than 1, then what do I expect to happen? So the last one dominates. So let's see what comes out. So we have c times n to the d times the last one. So let me just kind of rewrite the last one. A divided by b to the d, everything log b n. OK, well, it's a bit of a big mess here. So let's try to clean it up. So first, the c, whatever, like it's just a constant. OK, so let me just write big O. N to the d, OK, well, he looks nice enough. Let's leave him around. A to the log bn, so I can do the switch trick, right? So I can write n to the log ba. So this is just the numerator, right? I can also do the switch trick on the bottom, right? So that would be n to the log yeah, that one requires an extra step. Let me try to make it explicit. So the bottom is b to the log b n to the d. Do you agree? Right? Because d goes in front of the log, right? And it hops inside as an exponent, right? Because logs are weird. So when you take the constant in front, you can put it inside, it becomes the exponent, OK? So now we have b to the log b n to the d. Now I can do the switch trick, right? By the way, it's not called, I just made it up the name, right? So you can call it what you want. This is the switch trick. And the bottom becomes n to the d, right? Because I'm just switching these guys, OK? And it's n to the d to the log b of b, which is 1. OK? So these two guys cancel. And the answer is n to the log ba. Is it consistent with what we wrote earlier? Yes, because a was 3, b was 2, and we get precisely that. OK? Is it consistent with the previous answer? Yes, because a was 4, b was 2, and we get 2. So both of them fell in that case, right? Now, the other two cases are much simpler. So if a to the bd equals 1, then what do I expect to happen here? So we'll have c times n to the d times what? I mean, many ones, right? How many ones are there? I'm summing them up. I have log bn ones, right? So log bn. And in asymptotic notation, this is just n log n. Sorry, nd log n, right? Because the base of the log doesn't really matter. It's just only a scaling factor of the log function. Notice that it does matter when it's in the exponent. But when it's just sitting around there in the bottom, it's just a scaling, right? So it's just n to the d log n. And in the last case, a divided by b to the d, when it is less than 1, then I have c times n to the d times order of 1, right? Some sort of absolute constant. And this entire thing is n to the d. OK? So these are the only things that will pretty much ever show up in the entire course. OK? So please remember them. OK? All you really have to remember is that there is this ratio that controls this sum. OK? And the ratio is a divided by b to the d. OK? And if that thing is greater than 1, then you know that you have to account for the last term, the biggest one. OK? And in particular, so you get always this expression. If it equals 1, then you pick up a log factor, OK? Because everything equals 1 inside the sum. If this ratio is less than 1, then kind of the sum doesn't matter, and you just pay for this. OK? Intuitively, what's happening is that this is saying that the tree is top heavy. OK? kind of, most of the work is happening at the top of the tree, and you're paying the cost there. Okay? This is saying that a tree is kind of balanced. You have log bn layers. Each of them costs roughly the same. That's why you pay n to the d log n. Okay? And this is saying that the tree is bottom heavy. Okay? That most of the work is happening at the leaves. And it is pretty much the work that happens at the leaves already. Okay? And clearly, by sort of tweaking the constants a, b, and d, you get different types of trees. They have different asymptotic behavior. Okay? So kind of the punchline here is that, remember, at high level is tree. There is some, it's kind of the cheat sheet of what happens after recursion, right? But it's also helpful to have some sort of image in your hand that you can use to double check kind of what you're doing. Okay? Remember, sort of top heavy, balanced, and bottom heavy. Okay? Questions?
Read out the last two terms of A over B or B and
This one? The last two terms here? Okay, so let's see what happened here. So the C, we absorbed it in the big O. N to the D, still hanging around. The numerator, we have A to the log Bn. We switch A and N, and we get N to the log Ba. Right? Now, B to the D log Bn, well, we took the D, and we put it inside. So it's B to the log B of N to the D. All right? And then we just changed the denominator, and you realize that we can switch these two. Right? So we have N to the D to the log B of B. Log B of B is like log 2 of 2, or log 3 of 3, log 4 of 4, 1. Okay? So it's N to the D to the 1, okay? Or times 1, sorry. And this one cancels out, and this is the question, the answer you get, N to the log B of A. Okay? Yeah. More questions? Okay. So now you know how to analyze the running time of recursive algorithms. Please remember this. Honestly, this is not super exciting, so let's watch at least one. Let's see at least one algorithm today. Okay. So let's talk about that algorithm. So I'm going to switch gears and talk about an algorithm. Okay. So other questions about that one? Okay. But anyway, this one has, let's say, strong operational value. I mean, it will probably show up in a midterm, and probably any recursive algorithm you write down, you should be able to kind of. This thing also has a name, by the way. It's called the master theorem of recurrence relations, something like that. So in case you thought it was a puny theorem, it's not. So it's a useful one. So that's why somebody gave it an important name. Okay, so let's talk about an algorithm. And specifically, we're going to talk about more multiplication. But instead of talking about multiplication of integers, we'll talk about multiplication of another sort of fundamental object that shows up all the time, and that is matrices. Okay, so we're going to talk about matrix multiplication. Okay, so matrix multiplication. Okay. Guys, let's keep quiet. Another 20 minutes and you can go out. So what's the problem? We have as an input. What's the input? Two matrices. Two n by n matrices. So here they are. X and Y. Okay, so they're kind of n by n matrices. Okay, and what you want to output is their product. So what is the product of two matrices? Syntactically, a matrix. Okay, so how big is it? Also n by n. Okay, so to start from the basics. Okay, so it's an n by n matrix. Let's call it Z. Okay. And what is the definition of Z? So if I look at if I look at the ijth entry, what do I find there? Some treasure. No, what do I find there? Yeah. Yeah, you had your, sure. Excellent. Yeah. So in the ijth entry of Z, you find the dot product of two vectors. One vector is the ith row of the X matrix, and the other one is the jth column of the Y matrix, and that will give you this ij entry here. Okay, so one way to write it is just the dot product of x, I, so we can say star, meaning like, the ith row, and y sort of star j, so it's the jth column. Or to make it even more explicit, it's just the sum as k goes from 1 to n of x, I, k, y, k, j. Okay, that is the dot product of the ith row in X and the jth column in Y. Okay, so now I will not justify what somebody cares about. These matrices show up all the time, and you want to multiply them. Okay? Yes? Yes, I can try to do that. Also, next time what I can try to do is to bring some sort of thick chalk, which I kind of expected to find here. Let's try that. So, yeah, I guess. Yeah, maybe next time I'll try to do it from the beginning. Sorry, like I taught in Pimentel before, and not in this particular course, class yet. So, okay. So that's a concrete problem, okay? And we would like to produce the output as fast as possible. By the way, what's the best I can hope for in terms of speed? Like as a crude n squared, like I have to spit out n squared numbers. Certainly I won't be able to run say, linear time, okay? I should at least be able to output the object that I'm supposed to compute, right? So I have to pay at least n squared, okay? Now, we'd like to kind of get close to it as much as possible, right, to this best case. Now, there is a trivial algorithm or straightforward algorithm to multiply the matrices. Can anybody say how much it costs? So what's the straightforward algorithm to multiply the matrices? I just compute all the dot products one by one. Okay, it's a very boring algorithm. Okay, it says consider every I, consider every j, and then compute zij as the definition exactly says. Right? So this is basically taking the definition and turning it into an algorithm, okay? It says the definition tells you the expression for every entry in Z, and you just take each of the n squared entries of Z, and you compute it directly, okay? So the cost of this line is what? N, right? It's order of n. We're doing this n squared times, because there are n squared entries, and overall, this costs cubic time, okay? I would say, well, it's not n to the 100, so it's already something, right? But the question is, can we do better? Okay? Now, actually, it turns out you can do better, and you can do it via a recursive algorithm, very analogously to the way that integers can also multiply faster. So here's the idea. So the way you can find recursion in matrices is to think of slicing them up in so-called blocks, okay? So you view, for example, this X matrix, which is n by n, as made up of 4 quadrants of size n by n over 2 by n over 2 each. And you think of x that way, you think of y this way, you think of z this way. So now you think of x, y, and z as made up of each 4 blocks. If you do it, then essentially what you're asking is multiplying two things that look like this, a, b, c, d. You can think about these as integers or as themselves matrices. And you multiply them by, say, E, F, G, H. OK, these are the quadrants, the blocks. So this is x times y. I have just written it this way. And I can just use the fact that a kind of matrix multiplication has this blockwise structure. I can actually write the product of x times y as in terms of these sub-blocks, right? So there is the top left quadrant of z will be what? So what is the top left quadrant of z? So z itself is, let me write a bit bigger here. Z itself, I want to view it as having 4 quadrants. What should I write in the top left here? So it's like this thing here, right? So it's AE plus BG, right? Right? And then if I want this entry here, it would be the first block row so times the second column, block column here, right? So it's AF plus BH. Right? And I continue this way, so CE plus DG. OK? And CF plus DH. Okay, let's just kind of make sure syntactically what we're doing makes sense. These are n over 2 by n over 2 matrices. When I multiply them, I still get n over 2 by n over 2 matrices. So this entire thing here is an n over 2 by n over 2 matrix. So it makes sense to put it in the top left block of something that is n by n. Similarly for these other guys, and when I assemble all these blocks, I get back z. Where is the recursion here? I have subproblems, right? How many subproblems do I have? No, I don't have 4 subproblems. Look harder. There are 8, right? Because here, what are the subproblems? They're matrix multiplications on things that are smaller, right? So how many products are there? 1, 2, right? So because this entire block here actually requires 2 multiplications. 3, 4, 5, 6, 7, 8, right? So this expression gives you recursion that looks as follows. It's Tn 8 times Tn over 2, right? Because I'm halving the size of my problem. And at each combination step, what do I pay? Sorry? N squared, right? Because I'm just adding up matrices. And adding up, you just do it entry-wise. OK? So n squared. That is our recursion. OK. I don't think anybody wants to write down a tree for this one. We can just use the theorem that we have there, right? So what is the answer here? So let's look at this sort of ratio, A divided by B to the D. What is this ratio right now? So it is 8, right? Because A is 8 divided by 2 to the 2, right? So it's 2, this one here, and that's the other 2 here. Do we agree? Which is greater than 1, OK? Because 8 divided by 4 is greater than 1. So in which case are we here? The first one here, right? Which says, OK, if you're in this case, blah, 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 what you should get is n to the log b of a. A was 8, b was 2, so log base 2 of 8 is 3. So unfortunately, we get, again, n cubed. But this is similar to what happened with the integer multiplication, where we it found the recursive structure, but we didn't really exploit it yet. Right? We still got an n-squared algorithm. Here, we uncovered the recursive structure of matrix multiplication, but we yet have to exploit it. It still gives us a cubic algorithm that is different than this one. I mean, you would code it up in a different way, but it has the same running time. Okay? So what we're left to do is to actually exploit the recursive structure to reduce, ideally, the number of multiplications. Okay? Instead of 8, we want to do less than 8. Okay? Is it clear in the plan? Also, is it clear this is n-cubed? Also, how we applied this theorem? Okay, see people nodding, so I'll take it as a yes. All right, so let's talk about how do we speed up matrix multiplication. So I want to save this one, put it up there, and I'm going to enjoy a very clean whiteboard. I mean, a blackboard, actually. So the idea of doing better than this is due to Strassen in the 60s. Okay? It's known as Strassen's algorithm. And very roughly speaking, you just stare long enough at this one, and you try to come up with some sort of intermediate computations, sort of P1 through P whatever, that will help you out, right? So in his particular case, what he came up with was sort of 7 magical expressions. Maybe I'll write them in a moment. P1, P2, P3, P4, P5, P6, P7. Notably, 7 is less than 8. By the way, why am I calling these things P? Because it means product. Each of them will cost you 1 product. Okay? And given these 7 magical products, he was able to take this expression here and rewrite it in terms of these products with just additions and subtractions. Okay? And the 4 quadrants kind of look like this. They're not very illuminating. I'll talk about this in a moment, but sort of the main point, it can be done. So okay, so I'm not sure I want to write sort of what these expressions are. Maybe I can give you a sense of what they are. The first few, a times f minus h. P2 is a plus b times h. Whatever, something. You take a couple of things, you add them up, you multiply them, okay? So the point here is that once you've done these 7 matrix multiplications in a subproblem, okay, there is some way to put them together using no more, you're not allowed to use the multiplication anymore. You're only allowed to do n-squared work. So that is n-squared work, n-squared work, n-squared work, n-squared work, okay? And actually, unlike the trick up there that you can totally eyeball it, right? So this thing here could be the subject of a reasonable homework, right? Just eyeball something better, right? Strassen's algorithm is actually a bit of a curiosity in the literature of computer algebra, because it's just, he himself found it basically by brute forcing. And, but okay, fine. So some things can be found by brute. Yes, there's a question. In the matrix is P5 plus P4 minus P2 plus P6, and then P1 plus P2, P3 plus P4, P1 plus P5 minus P3 minus P7. And it's in the book anyways. Yeah. Anyways, so this guy found it basically by brute force. And they say, OK, fine, maybe sometimes you find interesting things not through enlightenment, but just by a sheer will. So, and then there was a sort of an effort to try to reinterpret ex post why some funny-looking expression like this, specifically for 7, okay? Why not 6? Why not 5? Right? Maybe there's a better way to do it with 5 multiplications, okay? And there's actually a sequence of works that tries to sort of provide some sort of more concise, satisfactory explanations for why this works, because it clearly cannot really be eyeballed. And so yesterday I was looking at some paper. So this, every few years there is some paper about this subject. And so actually there was just one last year. I can write it down here if you're curious to look it up. It's called, guess what, Designing Strassen's Algorithm from last year. Strassen is S-T-R-A-S-S-E-N. And designing an algorithm, you should know. So because it's just from last year, and the entire paper, which is short, it's only 13, 14 pages, is about talking, where does these magical expressions come from, why do they exist, and the explanations are actually not really elementary. You kind of need to start talking about tensor ranks of operators over vector spaces and things like that. But anyways, the point being is that it exists, and what it does for us is that we get a different expression where 8 becomes a 7, okay? So let's understand at least the running time of this algorithm. 7 times Tn over 2 plus order of n squared. Okay, so let's look at this ratio, a divided by b to the d. So now we have 7 divided by 2 to the 2. Before it was 8 divided by 2 to the 2. Either way, it is still greater than 1, okay? Because it is still greater than 1, we are still in this case up here, right? So we're supposed to get order of n log, wait, what is b? 2, right? So, and here I get 7, right? Okay, so it's something. On the order of n to the 2.81. Okay, so definitely less than 3. You can see it here already, and this is an approximation of it. This actually feels like a small improvement in exponent, but you start running these things on somewhat medium-sized matrices, you start feeling that the previous algorithm really sucks. And this one does a lot better. Because think about the recursion tree. If you multiply by 7 every time as opposed to by 8, these kind of trees have very different size, okay? Because you're paying that extra factor at every layer, okay? So, and in fact, sort of now that you've seen something like this twice, it's sort of it's a good time to think about just how powerful of a paradigm is it? Think about it. Here, all that Strassen really did was to say he found a way to take a constant size problem, which is matrix multiplication on 2 by 2 matrices. And instead of saying I can multiply 2 by 2 matrices with 8 multiplications, I can do it with 7. That's a constant size problem. Okay? It says how many multiplications do you need on 2 by 2 matrices? Because these blocks, it doesn't really talk about blocks, right? It's really about 2 by 2 matrices. Just knowing how to solve 2 by 2 matrices faster through recursion implies an infinite improvement on all problem sizes, right? Because you're going from n to the 3 to n to the log 2 7. Okay, the ratio of these two numbers is something that depends on n that goes to infinity. So you have made an infinite improvement on all problem sizes. Okay? By just studying a constant size problem. And in fact, you can actually generalize this paradigm. And you could say, in general, if you were to come across some way, like if you were to find a way to multiply k by k matrices for some k of your choice, maybe 3, 5, 6, whatever, okay? In k to the omega multiplications, then you could, using the same recursion, obtain something that looks like t to the n, t of n. You have your k to the omega multiplications to combine the problems. Because you used k as your base, now you have n divided by k, plus order of, to combine them, n squared. And this entire thing would yield an expression that is a generalization of that one, which is n to the omega. So somehow there is a recipe, a very concrete recipe, to do better than that, which is study, I don't know, 10 by 10 matrices, okay? And find anything. It's a constant size problem. You could try many, many things, right? And if you make an improvement there, then you will improve the cost to multiply matrices of any size, okay? And in fact, the problem of matrix multiplication has a sort of long and sort of important history in computer algebra. And essentially, the way people make progress is they study this problem for k that is enormous, like 10 to the 100 or something. And there are yet different techniques. Obviously, you cannot write down 10 to the 100, even if you write very, very small. Like, it's really a big number. And then there are techniques to study how do you upper bound the best number of multiplications to multiply those constant size matrices for a very large k. And that would give the best asymptotic running times. They're just asymptotic. In practice, everybody runs Strassen. All right. Next time, we'll continue with more divide and conquer.